So sessions scheduled post lunch really have to have that interactive element in them, and Professor Manas ensured that we all are interactive throughout the session and enjoy it. Our next talk will be delivered by Professor Preethi Jyothi on what is ML and why should we care. It will give you a very brief level overview of machine learning and with more emphasis on speech and its applications. Professor Preethi, just a quick introduction of Professor Preethi. She is an associate professor in the computer science department at IIT Bombay. She was a Beckman postdoctoral fellow at the University of Illinois. She received her PhD in computer science from the Ohio State University. She obtained her B.Tech from the National Institute of Technology, Calicut, and she was awarded a gold medal for graduating at the top of her class in computer science. Her research interests broadly lie in the area of machine learning as applied to speech and exploring interaction between speech and text. She has received the Best Student Paper Award at InterSpeech 2012. Since joining IIT Bombay, she has received the Google Faculty Research Award in 2017 for her proposal on accented speech recognition. These were a very small fraction of her academic achievements. To know more about the interesting work that she's doing, please take a look at the webpage of CSALT. CSALT is the Computational Speech and Technologies Lab at IIT Bombay Computer Science Department. So yeah, without any further delays, please join me in welcoming Professor Preethi Jyothi to the stage.
Good afternoon, everyone. Okay, so the title of my talk was, what is machine learning and why should we care? But I think after yesterday's panel, it's very clear we all care. So I'm just slightly modifying it, and since I just have half an hour, I'm going to give you a very quick peek under the hood with an emphasis on problems in speech and language, because that's what I work on. So this is a very, very quick kind of schematic overview. I think many of you are aware, but okay, what are the main components of machine learning? So you have a model, which I'm denoting by this box, which has these toggle-like switches. And then you have a bunch of data, right? And the data is, you have features and corresponding labels. So this is the supervised setting. And with this data, the hope is that you have to find a configuration of these switches through some algorithm which decides which configuration of switches best imitates this data that was used to train the model, so that at test time, when I give it a new set of features, it can give me a meaningful label out. Okay, so this is the whole training setup where I'm actually using my available data to train the models. And then a testing phase, because this is truly where the proof of the pudding lies, that when I give you a new set of features which were unseen during training, are you able to give me a label which is meaningful or not, right? So this is just a very, very quick kind of schematic. So the main components again are, which are critical to ML, or what should your model look like, and what is the data that you're using to train the model. So, and then this very important problem of how do I find this best or optimal setting of switches to match the data. Okay, and so if I were to do this exhaustively, so these are toggle on off switches, which means I'll have to look through an exponential in the number of switches, number of configurations, to look through what could be an optimal setting. So this is very difficult and obviously not the way to go about this. So there are many kind of clever optimization algorithms that work well, and one which is used a lot currently is gradient descent, where the main scheme is that examples are fed in one by one, possibly in a carefully chosen order, and these switches you're only adjusting a few at a time. Okay, you're not adjusting all these switches at once. And here's what makes it even more interesting. So in ML, typically you're never working with binary switches, but you're actually working with knobs, like the knobs which are used to turn your fan, okay, the regulators. So these are continuous, right? So which means these are all real valued numbers. So this makes these problems even more interesting, because how do I now find, there is not even binary switches. So how do I find this optimal configuration which ensures that my model is learning, okay, whatever that means, quote unquote. So what kind of machines can learn well? Okay, so to characterize such questions, there are large fields called like learning theory, where you can very formally talk about what is a model learning, is the model learning well enough to translate to data which you see unseen data at test time. But there are perils when you're dealing with models and learning in models. So one big peril is rote learning. Okay, this is when you're studying for exams, something that you often hear from your instructors is don't mug, right, in our terms. So don't do mugging, and that's a problem also that holds for machine learning models. So if a model memorizes all the training examples, then if you see a training example and then you try to predict its label, is going to achieve a perfect score. Okay, so if you have perfectly worked out every single problem in your textbook and you see exactly one of those problems in your test, you're going to do really well. The true test is if you're given a brand new problem, then a test of your understanding is if you're able to solve that problem well. Right? So similarly, if I'm seeing new or unseen examples, rote learning doesn't really transfer well to new or unseen examples, and so that's not a really good model. So the moral is that good models should not overfit. So this concept of doing really well on examples that you saw during training, but this performance not translating well enough to test time is referred to as overfitting. And so the general kind of maxim which is followed is Occam's razor, which is that models should be simple. So you in our switches analog, you don't want too many switches because that will just memorize the exact patterns that are seen in your training data and then not translate very well to test data. So just to illustrate this, let me consider a very simple 2D set of examples. Okay, so here you have these red points and then you have the blue points. And assume that these blue points these two are demarcated by this ellipse. And say that my model is very simple. It's going to draw these axis parallel boundaries. So it's only going to identify these kinds of squares or rectangles. So regardless of how well I fit these points, there are going to be errors because the true decision boundary is actually an ellipse, right? So the inability to fit, because here the choice of my model itself was too simplistic, it was overly simple. So it's not able to fit well enough, so this is going to contribute towards test error. But what if I go the other extreme? So I make my model very, very flexible, so it's going to massively go into every nook and corner wherever it finds training points, and it's going to fit these training points really well. Okay? But even here, we run into the problems of overfitting. So it's going to fit very, very well to your training data, but what if I slightly perturb these examples? Because of the flexibility of my model, the fitting function is going to really change how this decision boundary looks just because of small perturbations in my training data. And so this also could lead to test errors. Okay? So when I'm actually evaluating on unseen examples. And then there's always noise in my data. And this is more or less irrecoverable error. So these are errors which anyway I cannot do too much about. So the main errors I want to try and combat are the errors which are coming from my model either being too simple or overly complex. Okay, so here there is this sweet spot that you have to try and identify. And of course, if there are problems like this, where you have images of sheepdogs or mops, and then regardless of how good your model is, even for humans, it might be hard to kind of do well. Okay, so let's very, very quickly, just to address the initial question of, why should we care? There are so many applications of machine learning. So just to run you through this very quickly. So even in search, currently, when you search for any query, you are also given alternate questions which people have asked, which are related to your question and that could be useful to you. This is ML at work, right? It's going and retrieving questions which are similar to your question, and the similarity does, underlying the similarity measure are ML trained models. Also, if you want to search effectively within articles, ebooks, if you want to search through very, very vast repositories of data, here also ML is very useful because you want to kind of compress all of this information effectively. So this is all largely under this sub-area of ML which is known as IR or information retrieval. Then of course you have all problems to do with images. So face detection, which is now more or less treated as a solved problem. So when you look at your photo albums, you can see that your faces are already tagged, and if you have labeled them in some one photo, the label will also propagate to other photos. And then image captioning, also detecting objects. So visually looking for objects in visual images, also detecting cars if you're trying to build self-driving cars, detecting other cars on roads. So these are all kind of object detection based problems. So this is all largely under the umbrella of what's called computer vision. Then you have your social media applications where Facebook recommends friends or ads. So all these recommendations are ML driven. All these sites that you visit, like say Netflix, Amazon, Flipkart, all of these use recommendation engines which are all ML driven. So these are recommender systems. Then you have your game playing systems. So Go, chess, poker. How many of you have heard of AlphaGo? Almost everyone, right? So this was kind of a major news headline a few years back, because there is finally an AI system that can beat the kind of world expert at Go. And then you have robots. Lots of robotics does not really employ ML, but there is ML employed in robotics as well. So robots playing soccer, a robotic arm. There was also a robotic arm developed by DeepMind which could solve the Rubik's Cube. Okay, so that's also ML driven. So this is another subfield which is game playing AI and robotics. Then you have these very large machines like IBM's Watson. This is in 2011. So Jeopardy is this game where you have to kind of guess what the answer is. So for instance, there could be a phrase like, he was known as the father of the nation in India, and then you should respond as, who is Mahatma Gandhi? Because this was the game. And so in 2011, IBM built this large machine which beat the then top player in Jeopardy. Okay, so this was, so I thought this was funny in the context of yesterday's panel. So so this is Watson, which hands down beat the two world experts at Jeopardy, and he had under his answer written, I for one welcome our computer overlords. Okay, so this is even more relevant maybe today. So this also employed a lot of ML, and then currently there are these large medical diagnosis systems which also make use of ML to identify related medical articles and so on. Okay, so this is ML in expert systems. And finally, tying to kind of yesterday's panel, now we are seeing lots of interest, again, renewed interest in chatbots, also voice queried engines and machines, and also all of the videos you watch, if they have a closed captioning option that employs speech recognition at the back end. And in the pandemic era, we were all using conferencing tools like Zoom and MS Teams and so on. And all of these came with closed captioning so that you could also see the transcripts along with hearing the speech. Okay, so this is all driven by ML. And so this is under the larger umbrella of speech and NLP. So this is the sub-area in which I work. So I'm going to dig a little deeper here. Okay, so just very, very quickly, just to state what the speech recognition problem is. So this is credited to Fred Jelinek in the 1970s. So he was at Bell Labs, and he gave this formulation for the problem of ASR, which is a very long-standing problem. So this is this problem of translating speech into text, just transcribing it. And so he kind of envisioned this as a noisy channel problem. So let this boldface O be a sequence of acoustic features. Okay, and each of these features, just think of them as some informative features of the underlying speech, and then W is my word sequence. Okay, so if I wanted to formalize this optimization problem, what I'm trying to find is the best word sequence that maximizes this conditional probability. That's the probability of W given O, which you can flip around using Bayes' rule and write it as this product. And you can further kind of add one more random variable, which is Q, and this Q here refers to a phoneme sequence. So think of phonemes as the equivalent of letters when you are writing. So letters are the units in your written alphabet. So similarly, phonemes are the units in your spoken speech. Okay, so if Q represents a phoneme sequence, then you introduce this Q random variable, and so then you'll have this marginalization. But now you have this product of 3 probabilities, and these 3 probability models are referred to as the acoustic model, because from this acoustic model is only focusing on probabilistically mapping speech, which is your O, to a phoneme sequence, which is Q. After which you have a pronunciation model whose job is to take this phoneme sequence and map it to a word sequence. And finally, you have a prior over word sequences, which is your language model. Okay, so these 3 in conjunction are going to give you a speech recognition model. So this is a pipeline model, right? Because you are treating these 3 probability distributions as separate. So there's an acoustic model, a pronunciation model, and a language model. All of them feed in to create this large search graph, which you're going to traverse over, and then identify what is the most likely word sequence for a given speech signal. Okay, so this is even today there are many of these pipeline systems that exist. And now we are in this regime of what are called end-to-end ASR systems. So let me throw away all these components. No acoustic model, pronunciation model, nothing. I'll just have one large neural network. It's going to take my speech features, a sequence of speech features, and it's going to give me a sequence of characters directly. Okay, so it's directly mapping the original optimization problem of interest, which is find me the W, which is a word sequence which maximizes probability of W given O. Okay, and I can do this now because I know how to train very large model capacity neural networks. So it's not that people didn't know that this was possible earlier. It was just not, people were not able to do it because we didn't have the kind of compute and resources that we have today. Okay, so now everyone more or less, if you have sufficient amounts of data, you train end-to-end models that are directly learning these mappings. Okay, so let's go from end-to-end to what is the status of using these end-to-end models for speech recognition and other language technologies for India. So again, SLT, the big challenge in India is that you have so many languages. Okay, so of course you have 22 official languages, but you have hundreds of scheduled languages, thousands of dialects. And this is the account from the census 2011. There are 1,369 mother tongues and 19,000 linguistic affiliations in India. Okay, so this is the kind of diversity that we are talking about. And all these end-to-end models only work well when there is lots of label data. Okay, so this is a graph from the Whisper models accompanying paper. So this is from OpenAI. And you can see from this graph, so on the x-axis you have the number of hours of label data, and on the y-axis is an error rate, which means lower is better, right? And there's such a clear correlation between the hours of transcribed data that you have. So each point here is a different language. So the amount of data, label data that you have, and the error rates that you are incurring on a test set. So the more data you have, the better it gets. Okay, so but this is totally infeasible when you're dealing with multilingual societies where you have largely varying dialects, lots and lots of linguistic variations in your data. It's very infeasible to just collect lots and very, very humongous amounts of label data for every variation, right? So this is a very interesting space to work on, and this is something which I just lifted out of the model card of Whisper, where they explicitly acknowledge this, okay, that we observe lower accuracy on low resource languages and also accents and different dialects of even high resource languages. So this is kind of largely the space in which I work on and I'm interested in. So I want to talk about one specific direction, which is that of accent. And so this is actually a quote from a Wired article a few years back, which said that voice is the next big platform unless you have an accent. And this is a histogram from this project from Stanford called Fair Speech. So here the blue bars refer to speech from black speakers, and the orange bars are speech from white speakers, and these are 5 different state-of-the-art proprietary speech recognition engines. So you can see these are error rates, and the error rates from the black speakers are almost twice as that of the error rates from the white speakers. Okay, so there's this huge disparity between speech from the black and white speakers, which is a big problem if these are speech recognition engines that are front-facing or public-facing, right? It's going to create huge disparity between users. So this is one problem that we looked at specifically, and I thought this is nice to highlight in the context of some of the questions we got in the panel yesterday, where students were asking, how do we compete with these large companies who have so many resources and such large repositories of data? What do we work on, right, in academic settings? So here's one such problem where we can treat these big models as useful tools that we can work with, and then look at how we can kind of, in conjunction with these tools, do something interesting. So the problem we looked at is, so say that we have these state-of-the-art service APIs which are doing ASR, but these are black box systems, right? Meaning I don't have any access to the internals of these models. I only have the transcription from these models. How do I say I have a local ASR system which is catering to specific accents? So say that I want to build an ASR system in my lab, and I'm very interested in the local accents in Maharashtra. So I'm going to only focus on data which is collected from speakers in nearby regions And this is my local ASR system. And then I have these black box ASR systems which will only give me the transcript. How do I kind of combine these two to maybe make my performance even better, okay, and target the specific accents of interest to me? So this so what we thought of is, can we build a kind of guided inference on top of this local ASR so as to adapt this black box ASR system to speech that is coming from some target accent that I am interested in. Okay, so this is a problem that we were interested in. So just to illustrate this, so say I have the Google ASR engine which gives me a transcription with maybe some confidence scores, but I don't know anything else about the internals of the model. And then I have my white box local ASR model over which I have full control. And the goal here is that can I use this service transcription to guide the inference from my local ASR model. This is joint work by my student Karthik, Abhijit, who's in the audience, and my colleague Sarita Saravagi. So we designed this guided inference algorithm which is very lightweight and just couples the black box ASR with this white box or local ASR model. And so this algorithm itself is fairly straightforward. So say that we have this local ASR system. It's going to predict character distributions for every speech frame. Okay, so this I'm going to denote by P1 to Pt. And so here's an example. So here I'm showing you only the character with the highest probability and the corresponding probability value. Okay, so here you can see that the prediction from the local ASR model was TOSTATD. Okay, so that there could be spelling errors because these are predictions at the frame level. And here when you have repeated characters, you can merge them. Okay, so this is just a frame level prediction. So now I have a service prediction. So my Google, I pass this through Google, it will give me some prediction. And I'll take that prediction and align it with my speech so that now I have a frame level alignment of the prediction that I got out of Google when aligned with my speech. Okay, so here's my prediction from Google. So Google actually recognized this as posted, the word POSTED. And if I align it, this is what my character level alignments look like. And now the only thing that we tried doing is, can I revise my original P, the bold P, which is the probability distribution from the local ASR, to selectively support some of the service characters which have enough coverage even in my local ASR's probability distribution. So here, for example, with doing this revision, let me point you to these specific characters. So if you look at T here, my local ASR gives it 0.99 probability. It's very, very confident it's a T. And if you look at the service, it actually predicts P, but P has very little probability from my local ASR model. So it's very likely that the service actually hallucinated this P. We talked about hallucinations yesterday. So why did it hallucinate the P? Because the service models have very, very strong language models internally. And so it didn't really know this accent, and it thought maybe posted is a reasonable thing to predict here. Okay, so even though P did not have enough acoustic evidence, it inserted the P nevertheless, because the language model really liked P to be inserted there. So here my local model doesn't like P at all. So then T gets retained. However, if you look at these two columns, here my local model predicted A, but only with a probability of 0.55, and the service predicted E with a probability of 0.44. So this is fairly sizable, which means that eventually E caught up, and the final prediction was actually E, which I borrowed from the service, which had enough support even in the local ASR's probability distribution. And so finally, I end up with a spliced version of a final prediction, which I am using from the service as well in conjunction with what my local ASR predicted. Okay, so that's why we call it fine merge, because we are able to do this merging at a very fine grained level. So just for some results, these were our error rates from Google's kind of Indian English ASR engine. So by the way, Google has different ASR engines depending on whether it's Indian English, Australian English, and so on. They actually label them as different languages, British English and so on. So we use the specific engines for speech in these target accents, and these were the error rates. And this was a state-of-the-art merging algorithm, and with fine merge we were able to get nice reductions in WERs. And so here you can see some anecdotal examples. So if the prediction from our service was soda beef time, and our local ASR said for a breeze time, while the reference is actually for a brief time, then find merge is actually able to merge breeze and beef to make it brief, okay, if that makes sense. And similarly, you can see here as well that it's able to do this kind of fine-grained merging and recover the correct word. Okay, so maybe I'll stop at this point and quickly ask if there are any questions before I move to another problem. So how do you get these probability distributions? Yeah, this is from our local ASR system. So it's trained using a loss function called CTC. So CTC gives you probability distributions at every time frame. So this we get out from our local ASR system. Yeah, sure. Yes. Mm-hmm.
In other areas of machine learning, if this is the problem is with data, and you don't have enough data, what we usually do is fine-tuning.
Mm-hmm.
So is there a specific reason? Is it because of the grammar and syntax and semantics and all of that the approach of fine-tuning cannot be used in this feature?
Oh no, so good question. Fine-tuning can certainly be used here as well. So if you have a fair amount of target data, then you can always use that to fine-tune and you benefit from it. But the problem is you may have limited amounts of data, and especially for speech, to capture diversity in speech samples, you need a fair amount of data. So just to give you a concrete number, to get some reasonably robust system, even in a single accent of a language, you need of the order of 100 to 200 hours of label speech. And so to collect that amount of label data for a specific target accent or a target dialect, that gets tricky. So you could, fine-tuning data, you could collect maybe 10 hours, but that will only get you so much out of that particular model. But fine-tuning works, yeah.
So the approach of what you are doing is essentially even with 10 hours of data, we should be able to train a model.
Yeah, exactly. So our local ASR is quite small in size. So the local ASR just works with how much of our data we have, and then we are trying to leverage the all the power that the service ASR has and only fix the small errors which are probably being induced by accents.
This is with different accents
Yeah.
in the same language.
Yes.
So this cannot be applied to two different languages or two.
No, not to different languages. So the dialects you could maybe try a little bit of this again, but yeah, there are challenges. This is specifically for only patterns, pronunciation patterns.
Also actually for different languages.
Languages, yeah. So languages now, because you have multilingual models which are pre-trained, so there it's pre-trained on very large amounts of unlabeled speech data, but which is multilingual. So there you can fine-tune with a small amount of labeled language data, and that is still useful. That is useful for sure, but there is still a large gap. So that's what I'm trying to convey, that you need fairly large amounts of data for it to do really well. So here, this is the title of a YouTube video I picked out, I think Indian Idol or something, that Piya Tause Naina Lage Ka Amazing Rendition Deliver Kiya is Audition Pay. So there is code switching, there is different scripts, there's transliteration, like everything is part of this particular YouTube title. Okay, and this is widely prevalent in multilingual societies, and this is referred to as code switching, which is still very much a challenge for computational models, okay, which largely treat inputs as being monolingual. So why not just treat it like a new language? Because it's hard to get access to large amounts of code switch data, and the way in which code switching can manifest in a single sentence, there's so much diversity. Okay, so the same Hindi sentence can be written in various different code switching variants. These are just 3, but there's so much diversity in how it can manifest. So one problem, so I'll take 2 minutes. So one problem that we looked at is, okay, since there is not a lot of code switch data, can we actually generate code switch text which is very diverse? Okay, and so this specifically, if you're interested, in the interest of time, you can check out, it's called COCO. This is with my students and collaborators at Google. So we try to generate code switch text while providing certain controls so that we can really have some kind of fine-grained control over how the code switching patterns render. Okay, and why is this important? Because when I'm interacting with machines, I can render these queries in various ways. So the code switching can happen in different ways. And also now say you're chatting with a chatbot and the chatbot is using code switch text, then the way in which it says it, there should be diversity. There shouldn't be code switching in exactly the same way. So this is why diversity is important. Okay, so let me just leave you with these are some of the examples that we were able to generate starting from a Hindi sentence. And these look like fairly natural code switched variants. So I'll leave you with this slide, which is that ML, of course, now there's a lot of interest because of these new things which are being released from these large companies. But I want to also make a plug that there are many, many new frontiers to explore. I know some of you are from other engineering fields and maybe even from the sciences. So there are lots and lots of opportunities to kind of explore ML in the context of problems which are as varied as language, sciences, engineering, even people, because ML only works because you have data, and this data doesn't come by magic. There's lots and lots of work that goes into creating these data pipelines, and that means you're dealing with people. Okay, so there's a lot of interest also in kind of doing better with managing these data pipelines. And then we talked about this yesterday, but in the context of large language models, safety, AI safety also becomes an important consideration. So there are many, many exciting frontiers to explore, and I'm happy to take other questions about the material I talked about offline. So thanks everyone.